Good morning, class. Here's Chapter 4, Application of Derivatives, Section 4.6, Antiderivatives. We've covered maximum and minimum values, how derivatives affect the shape of a graph, optimization problems, and now antiderivatives. Reminding you of differentiation formulas. dy dx is limit of delta y over delta x as delta x approaches 0, or f prime of x is limit of f of x plus h minus f of x over h as h approaches 0. We start with the definition. A couple of ways to define E is the limit of 1 plus 1 over n to the power of n as n approaches infinity, or E is a number such that the limit of e to the power of h minus 1 over h as h approaches 0 equals 1. The power rule, the derivative of x to the power of n is nx to the power of n x to the power of n minus 1. And then we go to trigonometric functions. Basically, what these properties tell us that the derivative of x is 1, and if you want to differentiate, you do term by term. Product and quotient rules, chain rule, the composite function y equals f of g results in the differentiation y prime is f prime of g of x times g prime of x. And in Leibniz's notation, dy dx is dy du dx. And the power rule, which was the derivative of x to the power of n is nx to the power of n minus 1. The extended format would be the derivative of g of x to the power of n, which is n g of x to the power of n minus 1 g prime of x from the chain rule. Exponentials. The derivative of any exponential format is itself. If it's e to the power of kx, also times x. If it's e to the power of g of x, times g prime. And if the base is not e, times ln b as well. Then logarithmic formats, the derivative is the reciprocal. If it's a function of x, 1 over g of x, and then times g prime by the chain rule. If the base is not e, also we tag along 1 over ln b. When we pick 2 points, p and q, on a function y equals f of x, as we move from p to q, we cover a distance of delta x or dx or bp. And as we move from p to q, along the curve, the rise, delta y is bq, or f of x plus delta x minus f of x. And the rise along the tangent line is dy, or ab. And dy is precisely f prime of x dx. And delta y is precisely f of x plus delta x minus f of x. Sometimes it's difficult to evaluate delta y. It's replaced by dy as an approximation. Also, when we want to find the equation of a tangent line, one may refer to it as linearization. So linearization simply means find the equation of a tangent line at a specific point. And now 4.6, antiderivatives, also anti-differentiation, also integration. Calculus has 2 parts. Differential calculus, which deals with instantaneous rate of change and slope of a tangent line, and integral calculus, which deals with accumulated change and area under a curve. Both parts rely heavily on the concept of a limit, and they are intimately related. Integral is the opposite of a derivative, also called antiderivative. The question is, given the derivative of a function, what is the original function? That is the process known as antidifferentiation or integration. And so the antiderivative of lowercase f of x is the set of the function capital F of x plus c, such that the derivative of capital F of x plus c is lowercase f of x. The constant c is called the constant of integration. Antidifferentiation is often called integration. To indicate antiderivative of x squared is x cubed over 3 plus c, we write in the following format. The integral of x squared dx is x cubed over 3, or 1/3 x cubed, plus a constant. Now, what is this symbol? This symbol was introduced by Leibniz and is called an integral sign. It is an elongated S. Think about S and make it elongated. Looks like that, and was chosen because an integral is a limit of sums. In general, the integral of f of x dx is capital F of x plus c. Capital F of x plus c is the general form of the antiderivative of f of x. It's called the general solution or the indefinite integral. If capital F and capital G are any two antiderivative of f, then capital F prime is lowercase f of x. Capital G prime is also lowercase f of x. Then g of x must be capital F of x plus some constant, meaning because the integral is not unique, there are infinitely many solutions. So if we come up with two solutions, they only differ by a number, by a constant. Let's do this by a warm-up example. Determine these indefinite integrals, that is, find the antiderivative of each integral. So it's known as indefinite integral. In other words, 8 dx. Think of a function, you differentiate, it gives you 8 with respect to the independent variable x. That's the purpose of dx. So it's 8x plus c. And to prove, you check. How do you check? Reverse process. Differentiate the result. As you can see, the answer is 8. And c is a number. The integral of 10x to the power of 9 dx. Think of a function. You differentiate, gives you 10x to the power of 9. The answer is x to the power of 10. And we add a constant. Because it doesn't matter what number we add, the derivative remains the same. So we check by differentiating the right side. And we get the integrand, of course, without the dx. The integral of e to the power of x dx, think of a function. You differentiate, it gives you e to the power of x. And of course, it's e to the power of x. So the answer is e to the power of x plus a constant, everybody. To prove that, all we have to do, differentiate the right side. As you know, the derivative of e to the power of x is e to the power of x, and the derivative of a constant is 0. The integral of 1 over x dx, same thing. Think of a function. You differentiate, it gives you 1 over x. And the answer is a natural log. So natural log of absolute value of x plus a constant. Again, to prove that, we are going to differentiate the right side. And that gives us 1 over x. So the derivative of ln of absolute value of x plus c is simply 1 over x. We proved they are right. So this is the process. So let's go with basic the integration formulas. Let's find them. Reverse process. Because the derivative of kx is k and k is a number, is a constant, it's a multiplier, it's a coefficient, then the integral of k, of course, times dx must be kx. So the integral of k dx is kx plus a constant. The derivative of x to the power of n, we know it's nx to the power of n minus 1. Therefore, the integral of the right side, nx to the power of n minus 1 dx, must be x to the power of n. However, when it comes to the power rule, we want to look at x to the power of n rather than x to the power of n minus 1. So think about it. If it's x to the power of n, you want to integrate. What do you get? The integral of x to the power of n dx is 1 over n plus 1, x to the power of n plus 1, and a constant, and it can't be negative 1. It's important to know what happens here, the reverse process. Over here, we will subtract 1 from the exponent and multiply by, okay? Over here, we add 1 to the exponent and divide by, the reverse process. So let's look at this one. How do you differentiate x to the power of n? to get n to the power of x n minus 1, you do two steps. You multiply by n and you subtract 1 from n, right? The new exponent. Now, if you want to integrate that, it is the reverse process, meaning we are going to go this way, and 2 becomes 1. Number 1, add 1, so it becomes n plus 1. And number 2, multiply, becomes divide by n plus 1. And that's how we arrive at that. Okay. However, let me also prove that to you by looking at this right side and say, let capital F of x represent the right side. And now I'm going to differentiate. Capital F prime is 1 over n plus 1. And I want to differentiate this. So times n plus 1, x to the power of n plus 1 minus 1, plus the derivative of a constant is 0. And I hope you see this simplifies to simply x to the power of n. So we've proved that we've come up with the correct answer. So what is the power rule for integration, everybody? The integral of x to the power of n dx is 1 over n plus 1, x to the power of n plus 1, and a constant. We're going to look at more examples, and I'm going to erase my work. So let's start with the first one. If the derivative of e to the power of x is e to the power of x, the reverse process is the integral of e to the power of x dx is e to the power of x and a constant. If the derivative of ln of absolute value of x is 1 over x, the integral of 1 over x dx must be ln of absolute value of x plus c. Also, I want to remind you 1 over x also means x to the power minus 1. So either way. If the derivative of sine is cosine, then the integral of cosine x dx must be sine x plus a constant. If the derivative of cosine x is minus sine x, the integral of minus sine x dx must be positive cosine. But we don't want to put minus. The integral of positive sine x dx must be minus cosine x and a constant. More trigonometric functions. Tangent gives you secant squared, so the integral of secant squared must be tan x plus a constant. Cotangent, differentiate, gives you negative cosine squared, so the integral of positive cosine squared dx must be minus cotangent x plus a constant. If the derivative of secant is secant tan x, the integral of secant x tan x dx must be secant x plus a constant. And if the derivative of cosecant is negative cosecant cotangent, the integral of positive cosecant cotangent must be minus cosecant x plus a constant. Don't forget you need the dx here. Now, the constant multiple rule works for both differentiation and integration, which means the k, which is a constant, remains whether you differentiate or integrate. Therefore, you can take it outside the sign, the integral sign. Same thing here. Sum and difference rules for both of them, differentiation and integration, simply mean whether you differentiate or integrate, do it term by term, adding, subtracting, you name it. If the derivative of e to the power of kx is itself times k, the integral of that must be itself divided by k. So the integral of e to the power of kx dx is 1 over k e to the power of kx plus a constant. And again, the proof is very simple. Just differentiate the right side. You get e to the power of kx. So having said that, we can use the power rule right here. And all you have to do, the integral of x to the power of n is 1 over n plus 1, x to the power of n plus 1. So 1 over 7 plus 1, x to the power of 7 plus 1, and a constant, which gives us 1 over 8, x to the power of 8 plus a constant. What about the integral of x to the power of 99 dx? We do the same thing. We're going to add 1 to 99. So we get 1 over 99 plus 1, x to the power of 99 plus 1. And of course, a constant. Of course, 99 plus 1 is 100. So the final answer is 1 over 100, x to the power of 100 plus c. You don't have to write this. You can skip that if you are comfortable with the concept. Now, when we did the differentiation on something like square root of x, we made it ready for the power rule by rewriting it as x to the power of 1/2. We do exactly the same thing here, everybody. You have to get it ready for the power rule. So having said that, now we follow the power rule. 1 over 1/2 plus 1, x to the power of 1/2 plus 1, and a constant. Now, 1/2 plus 1 is 3/2. 1 over that is 2/3. 2/3, x to the power of 3/2. Now, and a constant, of course. Now, what I want to mention, this is fine. If you want to put it back in this original format, you have two ways to write it. You can write square root of x cubed, or you can write square root of x quantity cubed. Okay, that is putting it in the same format that we receive. In some cases, we must. All right, we want to integrate 1 over x cubed, and even with the differentiation, we would do the first step the same, getting it ready for the power rule. We're going to bring it up and write it as x to the power minus 3 dx. So that step is just to make sure it's ready for that. That's all. There is no other reason for that. Now, we use the power rule, which means 1 over negative 3 plus 1, x to the power of negative 3 plus 1, and a constant. Needless to say, this is negative 2. And as far as a fraction is concerned, when you have a negative sign, normally we put it in the numerator or in front of a fraction box. X minus to the power of minus 2 goes down. So negative 1 over 2x squared plus c is the final answer, everybody. All right. You're going to move on. As mentioned, when it comes to exponentials, differentiation, we have to multiply by the coefficient of exponent, which is k. In the case of an integration, we divide by it. So the answer is itself divided by 4. And of course, a constant, because we are integrating. What about e to the power minus 3x? Again, the answer is itself. But we're going to divide by negative 3. So negative 1/3 e to the power minus 3x, and of course, plus a constant. E to the power of x over 2. It should be clear that it means e to the power of 1/2 x. Just to be on the safe side, we write it in this fashion. So we know that k, or the coefficient of x, is 1/2. Therefore, we're going to write as 1 over 1/2 e to the power of 1/2 x, or x over 2, and a constant. Now 1 over 1/2 It's the reciprocal of 1/2 or 2. So the final answer is 2 e to the power of x over 2 and a constant. So we dealt with the exponentials. Now we want to deal with, you know, in essence, resulting in logs. And to understand this, we are going to write 2 over x as 2 times 1 over x. So it becomes clear that you really are dealing with 1 over x, and 2 is just a coefficient, everybody. So just what is the integral of 1 over x? The x is the natural log, okay? And 2 remains as a coefficient. So 2 ln of absolute value of x plus a constant. So when we write it in this format, makes it very easy to see the answer. And the same thing happens here. We are going to rewrite this, everybody, so it becomes clear what we have right now. One half times 1 over x. So this 1/2 remains, and deal with it just as we did here. So 1/2 natural log of absolute value of x plus a constant. It's that simple. So rewriting in this case, in this case, and in this case should help see what we have to do next. All right, the integral of this polynomial according to differentiation and integration rules. You just do them term by term. So we're going to concentrate on the first one and never mind the rest. So we add 1 to the exponent because it follows the power rule, becomes 5. So 2 over 5, x to the power of 5. This one, the same thing. We add 1 to 3, we get 4. So 3 over 4, x to the power of 4. Same thing here. We add 1 to the exponent, I get 3. So minus 7/3 x cubed. Now, to make sure we understand what's happening here, I'm going to write this means x to the power of 1. So 1 over 1 plus 1, x to the power of 1 plus 1. So 1/2 x squared, okay? Now, you don't have to write it in this fashion. You should really see it's half of x squared. I just wanted to justify that. And of course, minus 5 means minus 5x and a constant. The integral of x minus 5 quantity squared dx. You have to raise this to the power of 2 first. That means a minus b squared is used. A squared minus 2ab plus b squared first, elementary algebra. We're going to square the x, we get x squared. And then 2 minus 2 times x times 5 is minus 10x. And then b squared, 5 squared is 25. So first thing first, we are raising it to the power of 2. Therefore, it becomes easy to integrate. So this, we're going to add 1 becomes 3, 1/3 x cubed. But what about this one? Again, I want to show you this is the same as that in essence. The exponent that is missing is 1. So you write minus 10 over 1 plus 1 x to the power of 1 plus 1, which means minus 5x squared. Plus 25 means plus 25x. And now at the end, we add a constant. So don't forget, we need to add a constant at the end, everybody. All right, we are going to move on, everybody. Whether we differentiate or integrate, the first step is the same. We have a fraction where the bottom is one piece, in this case, more specifically, one term. We make up one and two and three fractions. So the first one is just one. The next one is minus 7 over x, and the last one is 2 over x squared. We do that to make it ready for integration, everybody. Now, what else do we do? And that's important to understand. Just to make sure that this is understood, how we anti-differentiate or integrate, we're going to write it as minus 7, okay, times 1 over x, and this one 2x to the power of negative 2. Again, what we are trying to do is just to make sure everything is ready for integration or anti-differentiation. That's what we are trying to do. And so let's do it one by one. The first one, obviously, because the independent dx means the independent variable is x, that becomes x. The second piece is also easy. We can see minus 7 and then deal with 1 over x. So minus 7 ln of absolute value of x. And this piece, two over negative 2 plus 1. I'm going to use the power rule, x to the power of negative 2 plus 1, which makes it 2 over negative 1, x to the power of negative 1. And we write it as minus 2 over x plus a constant, because we don't want to have a negative exponent. And now we are done. So again, I'm going to erase my work and I'm going to recap. You make up three fractions and you make sure each one is ready so you can easily do the integration. One is easy. This is minus 7 times 1 over x. You write this as a power format, 2x to the power minus 2, and therefore use the power rule on that. Now, to integrate this, you notice the independent variable must be t because we have a dt, and therefore 1 gives you t. Cosine, remember the derivative is negative, but the integral is positive. The integral of cosine x dx is sine. So this must be plus sine t plus a constant. Again, cube root of x is not ready to be differentiated or integrated. The process is the same for both. The first step is to put it in a power format. So it's x to the power of 1/3. And now we can work on it using the power rule, everybody. So 1 over 1/3 plus 1, x to the power of 1/3 plus 1. That would be the power rule. Negative sign, you have two choices. You can say the integral of sine is minus cosine, or the integral of minus sine is positive cosine, or you say minus and then minus cosine x and a constant. Either way is fine. Now, of course, this becomes positive. Let's work on this one. 1 over 4/3, it's the reciprocal of that, and it's 3/4 x to the power of 4/3. Now, x to the power of 4/3, you can write it as cube root of x to the power of 4. So 3/4 cube root of x to the power of 4 plus cosine x plus a constant. This is just putting it in the same format. In some examples, they insist that you put it in that format. Also, you could This one, you could write it as cube root of x to the power of 4. That means the same thing. So I'm showing you various formats algebraically. Solve the initial value problems. dp dt is 2e to the power of 3 of t, and p of 0 equals 1. Please understand, this is an extra piece. We're going to discuss that in a moment. But for now, let's define the concept. Any equation containing a derivative is called a differential equation, short DE, and everything we have been doing in this section, without exception, they were all solving differential equations. A function which satisfies the equation is called solution to the differential equation. An initial value problem is a differential equation along with a specified value of the unknown function called the initial condition. So first and foremost, to make some sense out of this, let's completely ignore this and do what we have been doing so far, meaning I'm going to put the dt to the other side and say dp is 2e to the power of 3t dt because I want to integrate. And when I integrate both sides, the left side just gives me p of t, and I'm going to integrate the right side. The fact that it's an exponential, we have the same answer, but we have to divide by 3. So we get 2/3 e to the power of 3t plus c. So what you're looking at is the solution to the differential equation, but this is called an indefinite integral or a general solution. Why is this a general solution? Because we have this plus c. The function p of t equals 2/3 e to the power of 3t. You can graph that function, and this plus c takes it up and down along the y-axis depending on the value being positive, going up, or negative, going down. What does that represent? A general solution, infinitely many different functions. Now, with the help of one point, which has the coordinates 0, 1, we can find the c. Therefore, it becomes one solution known as the initial value problem. We are going to replace the independent variable, which is normally t or theta or x, in this case t, with 0, and the dependent variable, which is normally y or f of x, or in this case p of t, with 1. 3 times 0 is 0, e to the power of 0 is 1. So again, this is 0, e to the power of 0 is 1, and therefore 2/3 times 1 is 2/3, plus what number is 1? That becomes 1/3, and you are going to replace the constant here with 1/3. Now this is one of those solutions, is called a particular solution. So here we have infinitely many solutions for P of t. When we use one pair, we get to one of those solutions. That's why it's called the initial value problem. So with one initial value, we can come up with the answer. Here's another example. dy dx is 1 over x plus 1 over square root of x, where y is 5, x is 1. And again, this represents the pair 1, 5. This represents the pair 1, 5. We're going to completely ignore that first and write dy is the right side times dx. When I integrate the left side, I get y. And I'm going to integrate the right side by working on it. To do so, we are going to get everything ready for anti-differentiation. 1 over x is fine. 1 over square root of x is not. As you know, this is x to the power of 1/2 comes up, and now it's completely ready for the power. So the first part, 1 over x is simply a natural law. So this is ln of absolute value of x. This one, we use the power rule 1 over n plus 1. So 1 over negative 1/2 plus 1. X to the power of n plus 1, x to the power of negative 1/2 plus 1. And because we don't have anything else, now we say plus c. We are going to simplify. I hope you see that negative 1/2 plus 1 is 1/2. 1 over that is 2, so 2, x to the power of 1/2. So we have y equals ln of absolute value of x plus 2 square root of x plus a constant. And this is a general solution. It has infinitely many different answers. It is a family of functions, everybody. Again, just graph this one, and plus c, depending upon the value of c positive or negative, takes it up and down along the y-axis. Now we have one pair, 1 comma 5, that will help us find the constant. So we are going to replace the x with 1 and y with 5. As you know, ln 1 is 0. This is 1, so you get 2 plus c. 2 plus what number is 5? We get the value of c to be 3, and we replace the c, and a general solution becomes one of those solutions, particular solution. A quick recap, everybody. We want to solve an initial value problem. That means we have to integrate what's given, and that will result in a general solution. Very straightforward. The pair 1 comma 5 will help us find the value of c. So a general solution, infinitely many solutions, family of functions becomes just one of those. That's it. Uh, Another initial value problem. Find capital F of x such that capital F of 2 equals 1 and f prime of x is 3x squared plus 3x plus 6. So first and foremost, again, we're going to ignore that. And because we want capital F of x, we're going to integrate this, which means, of course, capital F of x is the integral of this piece times dx. You have to write it in this fashion, everybody. This one, 3 divided by 2 plus 1. 3 divided by 3, x over 2 plus 1. I hope you remember in the very beginning we did this. This is x cubed. This is 3 halves x squared, because remember the exponent is 1 here. So x cubed, 3 halves x squared plus 7x plus c. And again, we're done with the general solution, everybody. Yeah. Now this f of 2 equals 1, that means the pair 2 comma 1 will help us find the missing c. So let's plug in, replace the x with 2, replace the y or capital F of x with 1. So 2 cubed is 8. This is 4. They cancel each other. 2 times 3 is 6. 7 times 2 is 40. So as you can see, they add up. 28. 28 and what number adds up to 1? Negative 27. That's the constant. So replace it and it becomes one solution. So class, we have infinitely many solutions here. With the help of one pair 2 comma 1, we get one of those solutions known as the initial value problem. All right, let's integrate the integral of x plus 1 over square root of x dx. Even if we wanted to differentiate, the first step would be similar, in which case we have to replace the square root of x with x to the power 1/2 first. That's the first step, everybody. Make up two fractions and simplify each fraction. The exponent is 1. So x to the power of 1 over x to the power of 1/2 using the exponential rules, x to the power of 1 minus 1/2. Everybody knows that. So this is x to the power of 1/2. This is x to the power of negative 1/2. So all we've done a few steps, 1, 2, 3 of algebra. And now we are ready to do calculus, which means we're going to go with the power rule, everybody. So starting with the first one, 1 over 1/2 plus 1, x to the power of 1/2 plus 1. Same thing for the second one. 1 over negative 1/2 plus 1, x to the power of negative 1/2 plus 1. And since there is nothing else, now we add a constant. And believe it or not, let me box this. This is the only calculus step. We have done a few algebraic steps, and we're going to continue with more of algebraic steps. 1/2 and 1 is, of course, 3/2. Negative 1/2 and 1 is 1/2. Now you're dividing by 3/2, everybody. That means 1 over 3/2 is 2/3. 2/3. And this one, 1 over 1/2, that means 2. So this is 2/3 x to the power of 3/2. This is 2x to the power of 1/2 and a constant. You can leave it like that if you want to put it in the same format as this one. Of course, this becomes 2/3. Square root of x cubed, that's the first one, 2/3. Square root of x cubed plus 2 square root of x plus a constant. So again, we solve a differential equation, and the solution is an it's called an indefinite integral. The solution is a family of function, infinitely many solutions. Okay, not one, infinitely many solutions because of this constant. An application problem, example 7, a sample of cesium-137 with an initial mass of 79 milligrams decays T years later at a rate of negative 1.8249 e to the power of negative 0.0231 T milligrams per year. Find the mass of the sample after 23 years. Round your answer to one decimal. By the way, speaking of rounding, you do the rounding at the very last step. In between, you keep as many decimals as possible to come up with the correct answer. Having said that, what are we dealing with here? We are dealing with a radioactive substance, so we let m of a t represent the mass of that cesium-137 at time t or after t years. So what is given is this. This is the rate. This is the MDT, everybody. This is the derivative. The MDT is this. Negative 1.8249 e to the power of negative 0.0231 t. This is the initial value. That means m at t equals 0. M of 0 is 79. So we go through the process. We can find m of t. And then 23 years later, we want m of 23. So this is the given. The MDT is negative 1.8249 e to the power of minus 0.0231 t. M of 0 is 79. So we are going to find m of t and then replace the t with 23. So m of t is the integral of this times dt. In other words, you integrate dm becomes m of t, you integrate this one times dt. Now, as you know, when we differentiate e to the power of kx, we multiply by k. When we integrate, we divide by k. So the answer is itself divide by k. That means divide by the coefficient of t. We get negative 1.8249 divided by negative 0.0231 e to the power of the same power and a constant. You put this into a calculator and m of t becomes 79 e to the power of negative 0.0231 t and a constant. So that's a general solution. However, just like the initial value problem, as it indicates here, an initial mass, you use m of 0 equals 79 to find the constant. So if m of 0 equals 79, that means replace the t here with 0, and this becomes 79. Now, of course, when you do that, e to the power of 0 is 1. So you get 79 equals 79 plus c, and c must be 0. So m of t becomes simply 79 e to the power of negative 0.0231 t. And now, replace the t with 23 to evaluate it after 23 years. Now, we put it into a calculator, 79 e to the power of negative 0.0231 times 23. We put that into a calculator and we get 46 point, a bunch of decimals. Since we want one decimal, we have to know the second one. Since next to it is just 3, we just keep it intact. 46.4 units milligrams.